Okay, so if you remember on Monday, we had kind of this tedious derivation of the potential and the vector potential of a point charge and carrying out an arbitrary motion. We had said that let the trajectory of the particle be given by the function omega. This is the trajectory of the particle. It can just do an arbitrary motion. There is no restriction on the kind of motion it does. It can be accelerating, it can be moving at constant velocity, it can be at rest. Whatever this function omega of t is, the final potential expression we had at the point r at the time t was given by 1 over 4 pi epsilon 0, 1 over r minus r prime. Well, if the particle is at rest, this was the all of the story, r prime being the position of the particle. Let me write it in this form, omega of tr. But since now we also have this motion, we have an additional correction to here, minus r minus omega of tr dot the velocity at tr divided by c. So this was the new potential we had, and we also derived the vector potential. Vector potential is simply related to this phi. The relation was just multiply phi by v over v, v over c squared. Well, basically this c squared is nothing but mu epsilon 0. Epsilon 0 cancels this epsilon 0, and we have the mu times j creating this vector potential. And once you know the potential and the scalar and the vector potential, in principle, you just take the derivatives, etc., calculate the electric and calculate the scalar and vector potentials from these expressions. Now, what are these numbers? Let's say we are looking at the potential at this point r and t. The contribution to that potential will be due to my charge when it was at the point omega of tr. This is the point r prime, if you just call it r prime. This distance is r minus r prime. So this tr, the signal takes that time. We are looking at the time t. The signal to reach that point, it should be leave the position of the particle at an earlier time, and the distance in times was r minus r prime over c, which kind of complicates the derivations. So if you want to solve this equation, if you want to explicitly calculate this, you have to evaluate tr using that relation, and then substitute it over here, obtain the potential, etc. Now, one interesting case would be when we have any questions up to here. This is what we had done on Monday. Omega is the position. It is the function that describes the trajectory of my charged object. Now, one interesting case is the particle moving at constant velocity. I will skip the derivation. I mean, it gets boring, especially, I mean, for me it's fun to do the derivation because I forget it every time I do it, so it's something like learning something new. But for you, just watching somebody derive it, I mean, you are sleepy. So I will just jump it. If you are interested, the derivation is in the book also. In fact, the derivation of the general, for a general motion is in the book, The Electric and Magnetic Fields. And in the case of this motion with constant velocity, there's something interesting. The electric field, Q over 4 pi epsilon 0, times, I will define what this r hat is. Well, this is basically the electric field if the object was at rest. There is a small correction 1 minus v squared over c squared. Well, you see, if in modern physics, you are probably familiar with these factors, 1 minus v squared over c squared appearing everywhere. So here we didn't do any special relativity, but from Maxwell's equations, we automatically get those factors. Divided by 1 minus v squared over c squared, again, sine squared theta. And this vector r is nothing but, r is the position at which we are observing the electric field, and omega is the function that is describing the trajectory, but evaluated not at the retarded time at that time. We are observing the electric field at the point r at the time t, so this t over here is the time at which we are observing it. Now, it doesn't mean we are ignoring any retardation effects, etc. All of those effects are taken into account, and the electric field just turns out to be along this direction. So this is the position at which I am observing the electric field. This is the position of the charged object at the time that I am observing the electric field. So you see, the electric field is again radial. It's just pointing from, although my charged object is moving, it points from the position of my object radially outward. It is not homogeneous. It points at different directions at different points. You see, the maximum that this fraction gets is when this is maximum when here we have the smallest. The smallest is the maximum of the sine squared theta. Theta is the angle between my observation point and the velocity. So this is electric field is maximum when sine theta is 1. And sine theta is 1 when theta is pi over 1 or minus 1. So the electric field is maximum at the perpendicular distance to my charge. And it is at a minimum when this factor is largest, so that is when theta is equal to 0. That is just ahead of my charge and at the back of my charge. And if you would draw the electric field lines, so this is my charge at the time t. It is maximum when theta is pi over 2 or minus pi over 2. So it's maximum in this direction, it's moving in this direction. This is the velocity of my particle. They are kind of bunched in the vertical plane vertical to the velocity, the electric field lines. And the magnetic field for this case is just 1 over c squared v cross E. Now, you see, before we had the question at the beginning of the semester, at the end of the last semester also. You see, you have these two charged objects. Just for simplicity, they both have the same charge. They are at rest in one reference frame. So what will happen is they will just accelerate away from each other. Now we can go to an alternative reference frame. Now in this alternative reference frame, let's say they are moving with a velocity v. Now if you look at the magnetic force, the lower charge will create a magnetic field at the position of the upper charge pointing towards you. Let's say this is B of the lower charge. So that charge, assuming all the charges are positive, that charge will feel a force in which direction? Downward. There will be a downward force. Now, if you do the same thing for the lower charge, the upper charge will create a magnetic field pointing into the screen. This is the B created by the upper charge at the position of the lower charge. So it will feel a force towards the other charge. So you see, there is this additional force, let's say, that is attracting these two charges. Now, of course, the acceleration in both of these reference frames should be the same. So the electric force should be larger in the second reference frame. And in fact, this is why in the second reference frame, the electric force is larger. Because you see, the electric force just above and just below the charge is larger. So there is a larger repulsive force due to the electric component and a non-zero attractive force due to the magnetic component. And at the end of the day, we get the same acceleration in both reference frames. So everything kind of turns out to be consistent. If you allow them, if there are no other forces, they should spread out. You see, there are two forces. This is the magnetic force. And there is also the electric force. The electric force, you see, in this reference frame, there is no magnetic force. They are definitely moving away from each other. So it should be the same in that reference frame also. Any questions?
Şu hocam elektrik fiildi yazarken şeyi mi kullandık acaba? Bu minus del fiili mi kullandık?
Yes. We already know the potential. So the electric field, given the potentials, is minus the gradient of phi minus dA by dt. And B is the curl of A. Well, the reference frame B, the second reference frame, is moving towards the left in reference frame 1, relative to reference frame 1. You see, just consider the reference frame fixed on me. I look at these two charges, they are at rest. Now I go to another reference frame, moving with a relative velocity, so I start moving in that direction. No, they are not. These are the forces. These are the accelerations. Now I am moving, and according to the reference frame at rest on me, those charges are moving in that direction with the same velocity.
Hocam aslında o şu şeyler yok aslında manyetik alanlar.
Why not? You see, here we have two different reference frames. In this reference frame, there is no magnetic field. There is only electric field. Here I have another reference frame. In this reference frame, there is a magnetic field and an electric field. Both of them exist in this reference frame.
Ama o reference frame'de observer hareket ediyor. Parçacıklar gene at rest.
So this observer, you see, if you want to say that something is moving or at rest, you have to first specify a reference frame. Without specifying the reference frame, they don't make sense. So in this reference frame, the charges are moving, and hence in this reference frame, I should be observing an electric field and a magnetic field. In the other reference frame, those charges are at rest. There is no magnetic field. So this kind of tells you that the existence or non-existence or the magnitude, let's say, or the direction of the magnetic field itself is a frame-dependent quantity. Just like velocity depends on the reference frame, the magnetic field and also the electric field depends on the reference frame. Now then there is this question. We already know in mechanics courses we studied how the velocities transform from one reference frame to the other reference frame. So how does the electric and magnetic fields transform from one reference frame to the other one? So that is something we will study in a couple of weeks. In which reference frame? You see, now we have this concept that if you want to talk about electric or magnetic field, you have to specify your reference frame. Just like if you want to talk about velocity, you have to specify a reference frame. So which reference frame are we talking about? So the one in which the charges are moving. Since they are moving, they will create a magnetic field. No, those are the magnetic fields created by the charges. So this is the magnetic field created by the upper charge at the position of this charge. This is the magnetic field created by the lower charge created at the position of the upper charge. There is no external magnetic fields applied. Now, before closing this chapter, there is just one more topic I would like to discuss before the exam, the forces. Well, we wrote the electric field in terms of the potentials, the magnetic field in terms of the potentials, but what about the forces? How can we express them in terms of the potentials? Now, let's see, the force acting on a point charge is equal to QE plus V cross B. V being the... Okay, there is one thing we have to pay attention to though. So what we are considering here is we have a point charge moving around. So the force acting on the charge will be related to the electric field at the position of the charge. My charged object is at the point R of t at the time t, so I need the electric field at that point. Plus the velocity of the object at the time t, cross product with b, again at the point, at the position of my charge at the time t. Now, they will be important because when we take, for example, the total time derivatives of a function, let's see, eventually we will need them. Let's just look at some function that depends on the position and the time, and the position is time dependent. And if you look at the total time derivative, well, there is explicit time dependence. The time dependence of the function, part of it will be due to that explicit time dependence. But there's also the implicit time dependence over here. So that is basically derivative of f with respect to xi times the derivative of xi with respect to t. Or written in a different form, plus v dot gradient of f. So whenever you see a function which depends on time explicitly and also maybe through the position dependence, the total time derivative will be the partial derivative plus v times the gradient of that function. Now let's go back to our force. The force is the rate of change of momentum. This is equal to Q times, well, E is the gradient of phi, minus the gradient of phi minus del A by del T, plus V cross curl of A. Let me try to get rid of these double cross products. Now V cross the curl of A is a vector. I can talk about its ith component, which will be epsilon ijk Vj curl of A, the k component, which is epsilon ijk Vj. The curl of A k component is epsilon klm del lam. I have the product of two Levi-Civita tensors, and that gives me Kronecker delta IL, Kronecker delta JM, minus Kronecker delta IM, Kronecker delta JL. I also have, Vj is over there. Vj del LAM, which is equal to, if we just take the products, Vj del IAJ, or let me write it, let me keep it this form, minus Vj del L del J AI. Well, you see, Kronecker delta IL multiplied with this one, it converts it to a derivative with respect to xi. Kronecker delta Jm multiplying Am just makes it Aj. And I'm summing over J. In the second term, Kronecker delta Im, Am makes it an Ai. And Kronecker delta Ja, Jl multiplied with partial derivative with respect to xl makes it a partial derivative with respect to xj. So V cross curl of A is just nothing but the gradient of V dot A minus V dot the gradient acting on the vector A. You see here, well, this is, it doesn't depend on position, it only depends on time, so I can just change the position derivative and the velocities. Vj, Aj is nothing but the scalar product of V and A. I'm taking the xith derivative, obtaining the ith component of that vector. Well, that is nothing but the definition of the gradient. And here I have the Vj del J, that is the scalar product of V and del, acting on the I component. Well, since I'm looking at the I component, that is the I component of the A vector.
Şurada del ile V'nin yerini değiştiremiyorsun.
I can. But you see, it's nevertheless, even if I change their order, it is the scalar product of these two first. Here it is the scalar product of these two first. These two things are different. These vector products are not associative.
Yani ben şu dediği ilk önce A'ya uygulayamam.
No. Well, in this form, yes. But in this form. Well, let's go back. This was our result, the force, which is the rate of change of momentum. This is equal to Q times minus the gradient of phi minus del A by del T minus V dot the gradient of A plus the gradient of V dot A. Well, look at this combination over here. I have the partial derivative, and here I have V dot the gradient operator acting on A. Those two terms are nothing but the total derivative of A with respect to T. So the total time derivative of P plus QA, there I have the minus QA, I just move it to the other side. This is equal to Q times minus the gradient of phi plus the gradient of V dot A. d by dt of P plus QA is equal to minus the gradient of Q phi minus QV dot A.
Şuna elektrik alanla manyetik alan gibi bir şey benziyor.
Well, not really. Well, the gradient of phi is just like the electric field, but it has the additional term which it lacks. I mean, we derive these from the electric and magnetic fields. Part of it is over here. Part of it is over there. But it does look like something else. Time derivative of something that contains the momentum is equal to minus the gradient of something that contains the scalar potential. Well, we can say that this is some kind of a potential. Let me call it U velocity dependent potential. And let me call it the capital P. It looks like the Newton's second law. Not really. It's the potential energy, velocity dependent potential energy, let's say. Now, in classical mechanics, you probably haven't yet studied the motion of charged objects. Did you? Well, this is have you heard of the concept of canonical momentum?
Lagrange.
In classical physics? Well, I mean, for the time being, this might not be making sense to you, but when you study the motion of charged objects, just remember this discussion. You will see that this is nothing but the canonical momentum for an object. This is the potential that you use in your Lagrangian. This will be the potential. You just add this term to your Lagrangian to study the motion of your charged object. And if you just take that term as your potential, you derive all the Lorentz force from your Lagrangian formalism. And if you calculate the canonical momentum corresponding to that Lagrangian, this will be your canonical momentum. As I said, if it doesn't make sense to you at the time being, don't worry, but just try to keep it somewhere in your mind when you study it in classical physics.
Bu equation of motion.
Yes. This is our equation of motion for a charged object in an external electromagnetic potential. This is my force, right? This line. This is the force acting on a charged object. Well, according to Newton, the force acting on a charged object is nothing but the rate of change of its momentum. So that is what I just rewrote it over here. This is the force, according to Newton, the rate of change of momentum is the Lorentz force is Q times E. This is the electric field. This is the V cross B. This is my E. And this is my B. I just wrote the Lorentz force. And then I reorganized the last term a bit to get rid of that double cross product. And in that case, the force acting on my charged object just took this form. One nice thing about this form is that, just look at these two terms, that those are nothing but the total time derivative of the vector potential at the position of my charge. Since that is a total derivative, on the left-hand side I have total derivatives, I just moved it to the other side. And at the end of the day, I get an equation just look like the Newton's second law. If I identify this thing as the as the momentum in quotes, it's called the canonical momentum. And if I identify this term as a velocity-dependent potential, you see up to this now, or up to this point, the potentials only depend on position and time. They don't depend on velocity. But to describe electromagnetic forces, we need a potential term that depends on the velocity. And in fact, if you want, have you studied Euler Lagrange equations? In classical mechanics, have you seen Lagrangian? And from Lagrangian, you derive the equations of motion. That's called Euler Lagrange equations. And if you just use this potential in your Lagrangian, add this term to your free particle, and derive the equations of motion. If you derive the equations of motion corresponding to this potential, you will derive the Lorentz force.
Ama hocam bu parçacık hani ışık hızıyla gidiyorsun orada.
Can it move at the speed of light? So what will be a problem even if it could go at the speed of light?
Yani klasik mekaniğin şeylerini kullanarak elektromanyetik şeyleri türetiyoruz ama elektromanyetik dalgada ışık hızı vermiyor.
No, we are not driving electromagnetism. We are driving the Lorentz force only. Now you can do that. That's another thing. But I mean, for the time being, what I am telling you is, just take your particle, put it in this potential. You will derive the equation of motion of your particle in an electromagnetic field. Now that is basically all I would like to discuss before your midterm. Any questions? On Monday or today? Here.
Aslında ikisi de aynı şeyi
Okay.
verecek yani fiyatlardan konuşuyoruz, potansiyellerden. Doğru üzerinden gelen aynı şekilde olsun. Objenin eşit uzaklıkta iki nokta olur. Birisi plus diye, birisi minus diye. Hangisindeki elektrik fiyatı da hangisindeki potansiyel daha büyük olacak?
So you are saying that at this instant, we just pick up this point and also this point. So what will be the magnitude of the electric field at those points? Let's see. They are at the same distance. So the magnitude of R is the same. One is at theta is equal to 0. The other one is at theta is equal to pi. So what is sine of 0? What is sine of pi? So this factor is also the same. So you see that the magnitude of the electric field at that point, let me give them names, at point A and at point B, the magnitudes will be the same. They are just pointing in opposite directions. So you see that the electric field is quite symmetric, because since sine theta is equal to sine of pi minus theta. If you take any point over here, the pi minus theta point will be just the mirror symmetric on the other side. If you imagine a mirror on this plane perpendicular to the velocity, it's the mirror image, and they both have the same magnitude of the electric field.
O zaman şey diyebilir misin? Yani equipotential line'larda circle.
Well, I can tell you that they will definitely not be circles.
Şöyle elips gibi.
No, hold on. So it will not be circles. You can also figure that out, that they will not be circled by, for example, looking at length contraction. In the rest frame, The electric field will be symmetric. It will be be the same in every direction. Equipotential surfaces will be spheres, and that sphere will be compressed if you go to another reference frame. Yes. Your other question?
No, that's all.
Okay.
Peki var mı olsa yani uniform charge distribution olsaydı?
Well, let's call this 1. Then just divide that charge distribution into very small bits, each moving at whatever velocity you assign them. Each bit will be a point charge, almost. Just write it, convert it to an integral. Since we already know the potential and the vector potential of a point charge, if you have a distribution of charges, just divide them into very small bits that can be treated as a point charge. And then sum them up, sum the contributions up.
Can we repeat the same question with non-constant velocity with an acceleration?
Sure. Look up your book, in your book. I mean, in your book, it treats the general case of an arbitrary trajectory and then specialize to a particle moving at constant velocity as an exercise. So let's give a 10-minute break, and after we will continue with your recitation, either on electromagnetism or classical physics.